Welcome to The Explainer. Today, we are breaking down the incredible science of how engineers design these massive skyscrapers to withstand the raw power of an earthquake. And let me tell you, it's a fascinating story of physics, really clever materials, and some seriously smart design.
Right off the bat, we need to get this crucial idea straight. The goal isn't to build an immovable object that can fight an earthquake head-on. That's a losing battle every time. No, the real genius is in designing an intelligent structure that can bend, flex, and safely ride out that violent shaking.
So here's our roadmap for today. We're going to build our understanding layer by layer. We'll start with the fundamental problem, then we'll walk through the standard rules, and finally get into the really advanced simulations and design philosophies that are keeping our cities standing right now.
Okay, let's dive right into our first section. Before you can even think about building a solution, you first have to get a handle on the basic physics that every single seismic engineer is up against. It all boils down to some pretty simple physics, actually. F equals ma. When the ground suddenly lurches sideways, the building's own massive weight wants to stay put, and that resistance, it creates this enormous force, an inertial force, that literally tries to shear the building right off its foundation. So the heavier the building, the bigger the force. So how do you fight that force? Well, that brings us to the absolute hero of seismic design, ductility. Here's a great way to think about it. A dry twig is stiff, right? You put a little pressure on it and it just snaps. But a green, living twig, that's ductile. It can bend and flex a long way, absorbing all that energy without breaking. And that is exactly what engineers want our buildings to do. All right, let's move on to our first layer of analysis and see how all this stuff actually gets put into practice. For most standard buildings, engineers kick things off with a simplified, rule-based approach that's been tried and tested for years. For most common, regular-shaped buildings, the starting point is a method called equivalent static analysis, and it's a really clever trick. It takes the incredibly complex, dynamic shaking of a real earthquake and simplifies it way down into a single, static horizontal force that you can push the building with in a computer model. And this is basically how it works. First, engineers calculate that total horizontal force at the bottom, which they call the base shear. Then, they just distribute that force up the height of the building, pushing on each floor. It's a really fast, really effective way to get a solid baseline for the building's design. But, not all buildings are simple little boxes. For the taller, more complex structures, engineers level up to something called response spectrum analysis. This method is way more sophisticated because it accounts for all the different ways a building can sway and vibrate during an earthquake, what they call its modes of vibration. Now here's the catch with all these linear rules. They're all based on one huge assumption, that the building acts like a perfect spring, always bouncing right back to its original shape. But we all know that in a powerful earthquake, that's just not what happens. Materials start to yield, concrete cracks, things get permanently bent, which of course brings us to our next layer. Okay, now we are getting into the really fascinating stuff, nonlinear analysis. This is where engineers stop using those simplified rules and start simulating what actually happens to the materials deep inside a building when they are pushed way beyond their limits. So, the crucial difference here is the question you're asking. Linear analysis just asks, is it strong enough? It's kind of like stretching a rubber band. Nonlinear analysis, on the other hand, asks, how is it actually going to behave when it starts to fail? That's more like bending a paperclip. Once you bend it, it stays bent. It's modeling real permanent damage. And the absolute pinnacle of this approach is the nonlinear time history analysis. This is where engineers build a super detailed digital model of the building, and then they hit it with ground motion data from actual recorded earthquakes. They can literally watch, second by second, as the simulation shows how the structure will bend, where it will crack, and how it absorbs all that energy. So what's the point of all this? Well, once you can accurately predict how a building is going to behave, you can do something truly amazing. You can start designing it for specific outcomes. We're moving away from just following a set of rules to actually setting goals for how the building performs. This is a total paradigm shift. It's called performance-based seismic design, or PBSD. Instead of just making sure the building checks all the boxes in the code, the building's owner and the engineers sit down together and decide upfront, exactly how do we want this building to perform in a minor earthquake, a moderate one, and what about a severe, rare one?
It's this whole iterative process, a design loop. You define your goals, you run those advanced nonlinear simulations to see if the design meets them, you evaluate the results, and then you go back and tweak the design. Maybe add a little strength here, a little more ductility there, and you keep doing that until it performs exactly how you want it to.
So at the very top, the highest performance level is called immediate occupancy. This is for those critical facilities. Think hospitals, emergency operations centers, data centers. The idea is that after a major earthquake, they need to be safe, secure, and ready to get back to work almost immediately.
Now, the most common target for commercial and residential buildings is life safety. Here, the building has done its most important job. It protected the people inside. It might be heavily damaged, it might need extensive repairs, but it did not collapse, and everybody got out safely.
And finally, the absolute bare minimum safety requirement is collapse prevention. This is for the most extreme, the most rare earthquake you can imagine for that location. The building might be a total loss, teetering on the very edge of failure, but it remains standing just long enough to prevent a catastrophe and save lives.
Okay, let's pull all these ideas together now. Let's see how they create this complete, modern toolkit for seismic design, and more importantly, what it all means for the future of our cities.
This table gives you a fantastic bird's-eye view of the whole process. You can see how engineers have this whole range of tools at their disposal, from the simple linear methods for an initial design, all the way to those complex nonlinear analyses for a deep dive, and right up to performance-based design, which shifts the focus from just forces to the final outcome, functionality.
And believe me, the innovation is not slowing down. Engineers are developing these incredible technologies that act almost like an immune system for a building. Things like base isolators, which essentially put the building on roller skates to separate it from the ground shaking, or dampers, which act like giant shock absorbers to just soak up all that seismic energy.
So this brings us to the final and maybe the most crucial point. The engineering goalposts are shifting. You see, in our complex, interconnected world, it's no longer just about survival, it's about resilience. The ultimate goal is to design not just buildings, but entire communities that can withstand a disaster, protect their people, and get back on their feet as quickly as humanly possible.